Welcome to another episode of Science Like Me. I'm Sara Naderi, the Outreach Director for the Halegiolu Data Science Institute at UC San Diego. Joining me today is Yinzhan Xu and Chris Ya. Yinzhan is a postdoc in the Computer Science Department at UCSD, affiliated with the EnCORE Institute and hosted by Barna Saha. Previously, he completed his Ph.D. at MIT, where he was advised by Virginia Vasilevska Williams. Prior to that, he obtained a BS degree in computer science and math from MIT. Welcome. Chris is a PhD student in Computer Science Department at UCSD, advised by Barna Saha and Russell Impagliazzo. He received a BA in mathematics from Princeton in 2021 and worked for 1 year at Morgan Stanley before starting his PhD at UCSD. Welcome, both of you. This is the first time we're doing two at once, so this should be exciting. We have a postdoc and a grad student, so I'd really like to know what the difference of that is. But let's get started. Who wants to start with sharing what their research is about?
I can start.
Okay.
So I do theoretical computer science, which is like understanding computational problems, but more from a theoretical perspective. So you can say what we are doing is more like math instead of actually program things. But under theoretical computer science, there are also many subfields. And what we are doing is more, it's called like fine-grained complexity. It's one of the things we're doing. Fine-grained complexity is like studying the relationship between different computational problems. So we ask questions like, why can't we improve this running time that has been stuck there for many decades, and whether we can find a reason or whether we can improve the current best running time.
Nice. So in that context, when you're trying to improve running time of computation, so the speed of the computer processing something, are you looking on a hardware level as well?
Usually we just abstract that out. There are many standard computational models like Turing machine and something called word RAM. And in some theoretical computer scientists, they also study like distributed computing. So there are different models. Some are like related to real life hardwares, but like in our research, we won't actually consider the time the programs will run on actual computers, but more like mathematically what's like a bound on the running time we can compute.
From where your research lies, when do you get to know it's working?
So I guess the work we do is like, we mostly try to like prove sort of how complicated a problem is. So like ignoring everything about like how you actually build your computer, what programming language you use, you want to be able to characterize how difficult a problem is. Ideally, the goal is like once you find the best algorithm, it's also simple and practical enough to be used in practice, which is the case for some problems, but like a lot of the times there's a sort of a gap between like the theoretically best algorithms and what's actually used in practice, just because it can be really complicated to actually program some of these things that, I don't know, like sort of are theoretically best, I guess.
There are many standard computational models like Turing machine and something called word RAM. And in some theoretical computer scientists, they also study like distributed computing. So there are different models. Some are like related to real life hardwares, but like in our research, we won't actually consider the time the programs will run on actual computers, but more like mathematically what's like a bound on the running time we can compute.
So when you take these concepts that you have developed, is there a process where you actually apply it and see if the running time has actually gotten faster?
I would say a majority of the work in theoretical computer science don't actually write a program and run it on a real computer. Okay. We're interested in like theoretically or mathematically what's the optimal runtime we can obtain.
Even if it's theoretical, I mean, at some point there's a stage in which it goes into some practical application, right? I'm really fascinated by this because I think that like there's so many different ways to try to make the computers work faster. Otherwise, people wouldn't be so interested in quantum computing, for example. I feel like that would be like hand-waving everything. We don't have to think anymore. But until we get there, it's almost as if like we have to be very careful what gets processed when and where and how. And I'm imagining that using math to do that can help you get insights into making those efficiencies just like a nanosecond faster here and there, right? Is that, I guess I'm just trying to understand from where your research lies, when do you get to know it's working?
So I guess the work we do is like, we mostly try to like prove sort of how complicated a problem is. So like ignoring everything about like how you actually build your computer, what programming language you use, you want to be able to characterize how difficult a problem is. Ideally, the goal is like once you find the best algorithm, it's also simple and practical enough to be used in practice, which is the case for some problems, but like a lot of the times there's a sort of a gap between like the theoretically best algorithms and what's actually used in practice, just because it can be really complicated to actually program some of these things that, I don't know, like sort of are theoretically best, I guess.
Let's talk about, I mean, are you guys doing the same kind of research?
Yeah, we work together a lot. So I guess we've been doing a lot of work on this problem, sort of like you're like comparing documents, kind of, and you want to like see how long it takes you to like compare two documents together. The formal problem is called tree edit distance, but so there's like some structure in your data as well. But so we did some work on that as well as along with our advisors and some other collaborators. And we've also been working on this thing called the attention mechanism, which is like sort of the subroutine in machine learning models that is pretty commonly used. And we're trying to understand like how best to basically compute this mechanism.
We also did an earlier work about like computing distance from a single node in a network to all the other nodes in the network. It's like from your home, you want to know how much time it will take you to the hospital, to a school, to a zoo, like everything else. So it's like single origin, but all the destinations. And we studied the computational complexity of a dynamic version of this distance problem.
Is that similar to like the traveling salesman problem, or is it a little different?
They share the similar thing, like they all concern distances in a graph, but the traveling salesman problem is much more difficult. It's like it's NP-complete. But this problem is actually can be solved in polynomial time, but we care about what's the actual polynomial time, like what's the exponent on the polynomial.
So you went from industry back to academia. I know that we're curious what that transition was like.
I'm really glad I came. I think grad school is I enjoyed working. I think my coworkers and everyone were really nice. But I think grad school, I get to like have more freedom and do things I enjoy. And I think also like the UCSD like theory group and like just I guess the general community is really great, and it's like a nice place to work and live. Yeah.
Nice. Are you thinking about going back to industry after?
Maybe, I don't know. I don't like to do too much like planning.
Yeah.
But I don't know. I would like to stay in academia, but it's also, I don't know. So I don't think it's like guaranteed or anything like that. So.
And how about you? You were at MIT for undergrad and grad school, and then now you're doing your postdoc. Can you explain what a postdoc even is? Because I feel like people think it's PhD and then you're done.
For me, postdoc is a good transition time between PhD and professorship. It's a time where I can just focus on research and do a lot more research after grad school. And because I know if I find a faculty position, I need to teach, I need to write grant proposal, and there are a lot of other responsibilities. But as a postdoc, I can focus on research. I think that's the main reason I'm doing a postdoc, and I hope that answers your question.
Yeah, I think it's I guess like the training wheels to becoming a professor, like you're saying. Most people who become professors have to do a postdoc somewhere before they become a faculty member somewhere. I visited MIT a couple years ago. It's a pretty cool environment, actually. How was it going from that kind of environment to UCSD? You have cool buildings over there. Like, I don't know.
We also have cool buildings here. We have a little house on top of a roof.
Yeah, no, we do, I guess. Yeah, no, yeah. But the environment, like the people, is it different? Like the culture in terms of MIT versus here? I mean, you were there for a long time too, right? 8 years, six years? How long did you, I mean, not that I need to ask that question.
4 plus 5, yeah.
Yeah.
9 years in total.
Yeah.
So I won't say there's a big difference in terms of culture, at least in the department I'm in. But I don't know the undergrad students' culture here, so I cannot really say a lot about that. But research-wise and like in terms of the group, I think both places are great. I don't think there's a very huge cultural difference.
What do you think you would want the general audience to know about why your research is so cool? What did I miss in trying to highlight about it, you think? Like if you were like a salesperson about your job, like, why is it so cool?
I guess first, I think it's really fun. I think the problems we work on are really interesting and something I enjoy like spending time on, but maybe like for more impactful reasons. So of course you want to understand like how, like if you have a problem you want to solve, you want to do it as quickly as possible. But for a lot of problems, it's really not clear what the best way to solve some problems are. And so you can either, give a nice algorithm and say this is a really fast way to solve this problem, or there are lots of problems where people have been like working for a really long time and just can't like come up with anything that's better than sort of, or I don't know, like the best algorithms from like the 80s or whatever. So like trying to come up with reasons that we can't do better than that. And you can sort of give like evidence or proof why these problems are so difficult, and sort of we're not just like we should turn our attention elsewhere and not like, well, I don't know if the lesson is to turn our attention elsewhere, but like maybe there's a reason the things we've been trying haven't worked, so we need to find something different. Right.
Is there anything you want to add?
So like getting back to the point where we do not actually write programs, but instead prove like theoretical complexity about problems. I think so a difference between like an n square running time and the n running time, maybe for some smaller n, the algorithm with n square running time is faster in practice. But like if the data grows bigger and bigger, and like computers are getting faster and faster, right? So like in many, many years, maybe the magnitude of data we are dealing with is very large, so that this running time with the algorithm with running time n, even though it like has very slow constants, it will eventually perform better than the algorithm with running time n squared.
I see. So your exploration of the data is about also like, there's like so many variables that so many parameters that you're looking at that can help give the programmer insight into which method might be better. It's not as straightforward as just using this particular method, because while that has been good so far, eventually it won't get that good. So I appreciate that, because I feel like the more we know about what's coming into this black box, then we can rearrange it to be more efficient for the output. And it's just like any little changes can make such a big difference in terms of efficiency. Like, what motivated you to want to go so deep into a subject? like, did you know you were going to dive that way? Or was it kind of like as you were going along as a kid, you're like, this is interesting. I'm actually okay at math. I'm going to do this. And then you're like, oh, it looks like being good at math has made it so that I could, go to this field. Oh, it looks like, was it kind of like you tumbled into it and it just kept getting deeper? Or did you know when you were a kid, I want to dive into that field?
Yeah, as a kid, I liked math, but I did not really know about computer science at all. So for me, it was more like I enjoyed everything related to math, but choosing this specific path is something I later decided.
Nice. That's cool. Then you got to you get to keep playing in the space that you like. What about math when you were a kid did you like?
It's hard to describe, like as a kid you cannot say why you like this toy, right? Why you like this particular book, but I just find math is very fun, and that's why I liked it.
I liked it because it made me feel safe. I felt like, I like to think of myself as an artist, but I feel like art is very subjective. But math was this very objective thing. So if you got the answer right, it was so gratifying because no one could take that away from you. You're like, it is correct, right? And then it gets harder and harder, and it gets challenging, and then sometimes not as easy, and then you work through it and you get there again. And it's like this journey that has a satisfying ending that's so objective, and it becomes this rinse repeat thing. That's why, I don't know, that's why I think math is cool. It's not always that's why I always get frustrated when people say they're not math people. I'm like, it's not, I don't think that's fair. I think you just have to try in a different way to get there. But that's cool. I feel like I can appreciate kind of hanging on to something that you like and then it turning into something later. When did you discover computer science would be an application that you wanted to apply it to?
Yeah, I started doing something called competitive programming in middle school, and I find the way to solve problems is very similar to the way to solve a math problem. And after we solve the problem, we also have to program things, program the solution, and we can submit it to a server to test whether the solution is correct. So compared to math, this is a more verified way to verify your solution, whether your solution is correct. So as you said, math makes you feel safe. So doing something like writing a program and can know whether it's correct immediately is another way to have this kind of feeling.
Yeah, I agree. That's cool. I appreciate that you tried doing a contest. You did a contest. Apparently you won something too, right, in high school?
Yes, in high school I went to something called IOI. It's International Olympiad in Informatics. That's the international level for high school students for this programming contest.
That's cool. I did a math contest once and I came second place. It was very sad. I was almost there. Yeah, it was. I was really surprised, just because the two smartest kids actually didn't come to school that day. So it probably would have been fourth place. All right. So, what about you? What motivated you to go down this path as a kid?
I actually feel I don't know. Whenever I got asked what I wanted to do as a kid, I didn't know.
Yeah.
I don't know. I've never really had I never really had a long-term I want to be this or that. But I did enjoy. I thought math was fun. I liked science and math and stuff. And eventually in college, I started taking some computer science classes. And those were also fun. So I actually never really thought about grad school until senior year so my college makes us do senior research kind of as an undergrad. And that turned out to be quite fun. And it sort of also made me think that this is something I could do. just 'cause I didn't really know what grad school was really until like basically senior year. So I think getting to know like what it was and that I could do it, and it seemed fun. I still wasn't like sure enough, so that's why I went to work. But I think also a lot of my friends from college who I think I like sort of looked up to ended up in grad school, and that was like another big reason I decided to apply.
Nice.
Yeah, and luckily Barnett and Russell decided to take me on.
Yeah. I think grad school is, it sounds like a lot. I didn't go to grad school. I didn't have enough interest in a particular topic to want to go to grad school for. But in terms of the lifestyle of a grad student, I always thought it was kind of cool. Like just a lot of hard work. But I do think it's pretty neat to be in an environment where you can passionately and very specifically go down a path. And just explore. I mean, you're explorers basically, and that's cool. I think it would be fair to say that no matter where in your educational journey, from elementary school to grad school, you had to stay working hard. And what motivated you to keep that kind of determination?
And I guess a lot of it is I do enjoy the things that I'm working on. So I think it's I think it's good. I think it's much easier to work hard if I find something fun. I feel like I actually don't have great determination if I don't like doing something. I think also it helped a lot. So my first sort of semester in college, taking real college level math classes, was very challenging. I just hadn't seen any of it before, and it just seemed like the classes were moving really quickly. But a lot of classmates who had at least seen some of it before, or maybe, I don't know, had some kind of more experience with that stuff, were super helpful. And just really nice about helping me out and helping me catch up. So that also I think is really finding some supportive group of people is really useful.
I love that you said that, because I think that's another one of those big things where people need to ask for help sometimes, and that's what helps them get further. It seems like it's a pretty straightforward thing to do, but I think sometimes it's challenging for people to ask for help. So I really think it's great that you found a supportive group to help you move forward. How about you?
Yeah, I completely agree with Chris that we need to like the thing we are doing and have a passion on our classes or even our jobs. And so it's a very important thing to keep us moving forward.
Is there any, I mean, like you said, it was challenging in that one class, but are there any classes that you had to do that you didn't like doing, but you still pushed through?
Yeah, but I guess the ones you have to take are usually more general.
Yeah.
So it's, I don't know, it's supposed to be doable for everyone, I guess. I don't know. It's less challenging, I guess.
Right. I think, but when you're motivated so much by something that you like, sometimes you will do the things you don't like so much just to get there, right? So you can keep having the fun research. So let's wrap things up with what you're looking forward to in the future.
So I guess one of the projects Yinzhan mentioned we worked on is this problem called dynamic shortest paths. So let's say you're at your house and you want to know where all the nearest, there's places you want to go, you want to know how quickly you can get to each of them. And Google Maps or whatever has to do this all the time for lots of people. So you want to do this quickly, but also roads change, right? So traffic can increase, roads close, lanes close, whatever. So you want to be able to update your quickest routes according to this. So you basically we're studying how quickly can you kind of recompute like given I know this road closed, find the newest, shortest path or something. So we kind of did some work sort of establishing kind of what the best algorithm for this problem was.
Nice. How did you, how did you figure that out?
So I guess we actually gave a lower bound, which means the best thing you can do is just recompute everything from scratch. And what's basically we said that if you solve this, you can solve another problem, which people have been trying and failing to do more efficiently for a long time. So like you kind of accept this other problem is hard, then this problem we want to solve is also hard.
Since you're a postdoc and you're a grad student, I know that you work together a lot. Are there times when you're working independently from each other?
Yeah, I mean, I guess we don't work on exactly the same set of problems. So there's some I work on, some he works on.
Would you consider Yinzhan your mentor?
Yeah, I think so. I think I'm glad he came to UCSD, and it's been really nice working with him. And he's really comes up with lots of nice ideas and is really fun to work with.
Yeah, I actually don't view Chris as a mentee. I view him as a collaborator. And he did a lot of great works and can always come up with nice ideas and give nice presentations, write nice papers.
Well, that's good. What's been the most exciting part about working in the EnCORE Institute?
Yeah, I think EnCORE is basically, I think, brings a lot of people together. So there's like a lot of workshops, a lot of kind of like mini sort of conferences, I guess, where you can like meet other people in the institute. And also I think it's done like a nice job bringing like speakers to UCSD and kind of get exposure to like things that I probably wouldn't have gotten exposure to otherwise. So I think it's a nice like resource for like connecting people and potentially establishing new kind of collaborations.
Nice. How about you?
I also agree that's the main benefit of EnCORE. Like also without EnCORE, I could not organize the workshop I'm planning to co-organize in May. And EnCORE provides resources and location to this workshop, and really appreciate that. And there are also other workshops at EnCORE that I am interested in attending. So it's really a great opportunity to bring other people and work with other people.
Thank you again for being here and sharing your research. And thank you for joining us on another episode of Science Like Me.